Hello everyone, good morning. This is Math 140, day 11. I want to talk about complex numbers and quadratic equations. So to begin with, I think it's best to start with a review of the shock that was the square root of 2. We have a perfectly fine equation, x squared minus 2 is 0, and there's no integer, not even a fraction that solves that equation. So people invented a number that would be a solution. And I want to call that number R. I know it's the square root of 2, but I want to call it R. Bear with me. And we want R squared to be 2, right? And once we've done that, then we have a solution. And the other solution for that equation is obviously negative R. And we can do math with it. You can do 3 minus R plus 1 plus 4R, which is 4 plus 3R. And we can also multiply those two. 3 minus R times 1 plus 4R. You FOIL that out, you get a 3. You get a 12R minus R and a negative 4R squared. At which point this property kicks in that R squared is 2. So the last term here is negative 8. We have 3 plus 11R minus 8, and it simplifies to negative 5 plus 11R, which means we've landed again at a number of the same form. That is a rational number, actually an integer even, but rational number, plus a rational multiple of R. And that's generally true. When you multiply two numbers of that form, you get another number of that form, because every time you encounter an R square, you replace it by 2. And so that's quite obvious. Whenever you add, subtract, and multiply in this set of numbers, you stay within the set. And then comes division. That's a little trickier. So let's divide. 3 minus R divided by 1 minus 4R. And here we did something like this before. Make the denominator rational. So we take this fraction, multiply top and bottom by 1 plus 4R. So it doesn't change the value. And now I've set up my example so that we've already done the multiplication in the numerator. See, that's just this previous problem which we just did. So I will get negative 5 plus 11R. And in the denominator, I see this pattern which leads to a difference of squares. So this is going to be 1 square minus 4R quantity squared. And 4R squared, the quantity 4R squared means both 4 and the R get squared. So I end up with 16 times 2, which is 32. And I've got 1 minus 32, which is negative 31. And you can rewrite this as 5 over 31 minus 11 over 31 times r. So it's again a number of that same form. A rational number, and then another rational number times r added to it. So this is quite important. This has far-reaching consequences. It means you can do algebra with this r, your 4 basic operations: addition, subtraction, multiplication, division. They all work fine. All the laws are still valid. Everything's good. And now we'll take this for a spin. Dull yellow line here. And instead of x squared minus 2 is 0, we start with x squared plus 1 is 0. It doesn't have a solution within the realm of numbers that we know. And so we just invent one and see where it takes us. And this new symbol is called I. And all we know about it is I squared should be -1. So I is a solution of that equation. That's all we know about it. But that alone means it can't be any of the numbers that we know so far. It's a new kind of number. And then you can form those sums and multiples, and they're also not numbers that we know. So we can do a plus b times I, and they will all be numbers that we don't know unless the b is actually 0, in which case you get the old real numbers back. So these new numbers are called complex numbers, and we can do algebra with them from the get-go by just saying all the laws that we know should still be valid. What laws do we have? X plus y is y plus x. You can switch summands. X times y is y times x. 1 times x is x. 0 plus x is x. So the number 0, the number 1, still does the same job that it does for the real numbers, for the complex numbers. So this takes a long time to check everything. We better practice working with complex numbers to show you that they're really not terrifying at all. Just like I did that example with this R at the beginning, you just have this I now, and you can add it. I see from Alex that a lot of you have already done that, so I'm gonna go right in with multiplying. Three minus I times 1 plus 4i. We FOIL this out. So it's 3 plus 12i minus I minus 4i squared, which is 3 plus 11 times I. It's ugly. 11 times I. And then 4i squared. The I squared is negative 1. So this is plus 4. Minus 4 times negative 1 is plus 4. So only in the last step is this example different from what I did with the square root of 2. Then let's divide. Three minus I divided by 1 minus 4i. The same technique, we want to make the denominator rational, so we multiply by 1 plus 4i divided by 1 plus 4i, which, according to laws, does not change the value of a fraction. Multiply top and bottom by the same quantity. And now that is in the numerator, this times that. We just did that, so that's going to be the same thing. It's 7 plus 11i. And in the denominator, we get 1 square minus 4i quantity square, which is 7 plus 11i divided by 1. What is 4i square? Quantity squared is 16 times negative 1. And we're subtracting this, so we get plus 16. And we can rewrite this as 7 over 17 plus 11 over 17 times I. So we again land on a number that's a rational number times this new symbol I. Had we started out with a real number plus a real number times I, we would have ended up with the same thing with real coefficients, guaranteed every single time. So that's good. It's just the same arithmetic with the one extra bit that I square is negative 1. Whenever you see I square, put a negative 1, and you're back home in the known bigger set of numbers. Okay, I should mention, maybe you noticed that, and I hesitated a little bit, with the square root of 2, we also ask that it should be greater than 0. And the other choice is the opposite, the negative square root of 2. The square root of 2 is always greater than 0. So we pick out of the two possible solutions for that equation, the one which is positive, to call that the square root of 2. And we do not have that with the equation x squared plus 1 equal to 0. So all we know is I is one solution, the other one is the opposite. And we can't say that either one is bigger or smaller or bigger than 0. So the notion of bigger and smaller is not defined for complex numbers. Okay. It doesn't hurt. If you notice, I mentioned this, the square root of 2 is greater than 0, but we never actually used that when we did algebra. Never in my entire example with those computations, did I use that square root of 2 was greater than 0. And so I don't need that to do algebra. I don't need it here either. But now let's solve a couple quadratic equations, at least one. X squared plus 4x plus 29 is 0. We're going to solve this. We could complete the square. We could apply the quadratic formula. So let me complete the square. X squared plus 4x plus 4. How much of 29 is left? 25 is left. So I've rewritten that equation. And this here is the perfect square. X plus 2 quantity squared plus 25 is 0. So x plus 2 quantity squared is negative 25. And therefore, x plus 2 has to be a square root of negative 25. If you don't know complex numbers, then you would say that just does not exist. If you do know complex numbers, you can say negative 25 is I squared times 5 squared. And so x plus 2 is a square root of that, and you can do 5 times I, plus minus. We don't know which. And we can subtract 2 on both sides. We get x is negative 2 plus minus 5 times I. Let's solve that same equation using the quadratic formula. The quadratic formula tells me I should take the linear coefficient, which is 4, take the opposite, then go plus minus square root of that linear coefficient 4 squared, that's the 16, minus 4 times 29. What is that? That's 126. 116, sorry. Divided by 2 times the quadratic coefficient, so 2. What is that? This is negative 4 over 2 is negative 2 plus minus square root of minus 100 divided by 2. Now, what is that square root of minus 100? The square root of I squared times 10 squared, which is plus or minus 10I. Right? If you didn't know that I was a weird complex number, you just think it's a variable, then you would just say, sure, yeah, that's what we did in module 1. And it's still true because all those laws about algebra are still true. That you can work with roots in this way, distributed over a product. Except that there's really no way of telling, is it plus or minus? You can't say it's bigger than 0 or anything. You've got to keep this plus or minus at all times. And that's also in the original equation, so we're good. We really can simplify, divide this by 2, we get x is minus 2 plus minus 5i. Same thing that we got with the completing the square method earlier. So that's good. You get the same answer. And this tells you that you can solve any quadratic equation with this quadratic formula now. Sometimes you get real answers if under the square root is something that's non-negative. Sometimes you get complex answers, that is not real answers. And if the question says include complex numbers in your answer, then you should do that. By default, we'll stick with real numbers. If you have a word problem, how long should the fence of my garden be that I'm going to build with this and this much material? You do not want an imaginary number as an answer. So if you get that, it has to be discarded. But if x can be a complex number, then include them. And I swear to you that there's real world problems where these numbers are not the answer, but they're useful for solving them. So they happen more under the hood, so to speak. They really help solving real world problems. Otherwise, we wouldn't put those on the syllabus. And they are a great exercise in algebra. I can't help it. This is just exactly what we've been doing in module 1 with variables. And now it's an I, and I square happens to be -1. Okay, that's it for complex numbers. We'll do more example in lecture.